All right, so what we're going to look at today, guys, is a bit of stuff to do with applications of the things we've been going over. Okay, obviously we've already gone over some of the applications like unbanked curves and bank curves and how we can use uniform circular motions that make those kinds of things. But we're also going to look at some other applications. They may not be as like real world kind of application, but they're still things that we're looking at and doing. Okay, and one of the things is something I just heard about yesterday, and it's NASA's newest launch. Them and SpaceX launched this thing yesterday, the double asteroid redirection test. Okay, this is a test of essentially our interplanetary space defense system. It's how we keep asteroids from hitting us. Right? So what this is kind of a proof of concept. They want to see if they can change the direction or speed or whatever of an asteroid by smashing something into it. Now, the physics of that would say, yes, you can. The question is, how much? Okay? We know that, yes, if you smash something into something else, you're going to cause an acceleration. There's a force there, okay? There's energy at work and all that kind of stuff definitely happening, right? But can we make that happen, okay, in a way that would be effective? And that's what this thing is all about. So they have found the perfect test bed, apparently. And it's this double asteroid system. So there's a big asteroid that's about 760 meters across. And it has a little moonlet, a little asteroid that orbits it, that's about 160 meters across. Okay? And that's the size that's worrisome, because 160 meters is big enough that it probably would get through and not burn up, and then could cause some damage, but small enough that we won't really see it until it's quite a bit closer than we would like. Okay? So what they're doing is they're sending this probe that looks like this, okay, to the asteroid, and they're going to smash it into the little one. Okay? And then they're going to watch, and they're going to time and see if the orbit of the little moon changes. What they're hoping is that they change the velocity and redirect that smaller moonlet enough that its period of orbit changes. Okay? So the time it takes for it to orbit the big one is going to be a little longer. Because what they're hoping is that when they smash into it, they push it a little further away from its parent asteroid. Okay? If they do that, then they have some idea of, how much they could change the velocity or path of an incoming asteroid. And then from there, they can develop bigger and better spacecraft to smash into asteroids to save us some other time. Right? So it kind of takes into account some of the things that we've talked about, energy and work from Unit 2, but also a little bit of stuff that we'll talk about later in this unit about orbits and how that relates to circular motion. Okay? So they got this spacecraft here, which it's a box with solar panels, okay, and this big engine. Right? So this engine is going to get it moving really, really fast, and I think it's going to hit it at like 6 kilometers per second. I think that's what it said later. Yeah, so it's going to fire up that little engine, 6.6 kilometers per second. Okay? Pretty fast. Okay? So it'll have a fair amount of kinetic energy based on its mass or its speed. Its speed, mostly. It's not very big. Okay? It's really impractical to launch heavy objects off of Earth, because the heavier it is, the more rocket power you need to lift it. Right? So something like this is not going to have a lot of mass. We want things to be as small as possible, okay? Because it's, I think, what did they say? It's like $1,000 per kilogram, okay, to launch something into orbit. So you kind of got to make the most of your mass, okay, in a situation like that. All right, so they've got this whole thing. It's going to be all like piloted on board, because obviously it'll be too far away, okay? But what they're hoping for is that when it hits, what's that back here? It'll change the orbital period of the moonlet by several minutes, okay, which is enough to be observed from Earth. So the impact won't actually occur until it's in range of Earth and we can actually view it effectively with Earth-based telescopes. Right now, that's what we see when we look at it. Okay, so this is kind of the bigger asteroid, and that's kind of the smaller one. Bigger asteroid, smaller one. These are kind of time lapse. Okay, so it's pretty fuzzy. Right? It'd be pretty hard to determine whether the period changes very much. We're hoping that when it gets closer, we can see it better. Like that's computer improved. Okay, so yeah, we don't see it well right now. Well enough to see the thing is orbiting and get an idea of the period. But what we're hoping for is that after it hits, that it'll take several minutes longer. If it takes several minutes longer, then we know that we've moved it several degrees from its previous path. Okay? And that's what we would hope for defending Earth from an asteroid. We don't have a hope of blowing up an asteroid. Okay? Even sending a nuclear weapon into space is a really bad idea because, well, our launch technology is not 100% reliable. And the last thing you want is a nuclear weapon exploding as it's being launched. Okay, kind of bad. So we don't want to do that. Okay, we want to just be able to use simple mechanical energy, okay, and simple Newtonian physics to make stuff happen. Right? If we smash something that's going really, really fast into something else, we might be able to make it move. And if we hit it early enough, that little tiny bit of movement might be enough to make it miss Earth entirely. Okay? If we wait too long and it's like, oh crap, there it is, like deer in the headlights, well, it's too late now. We can't move it enough to make it miss Earth. But if we can hit it when it's still a year and a half away, then we got a chance at moving it enough over the course of a year, okay, to make it miss. And so that's kind of what they're doing here, is just testing whether it's possible to change the path using all that work and energy, make that orbit take a little longer, the orbital period being a few minutes bigger. Yeah? So kind of the stuff we've been talking about. All right. So we're going to look at some circular motion stuff, but applications. We talked about the gravitron the other day when we were first talking about circular motion. We said that if it spins really, really fast, you can get pinned to the wall, right? And then you won't fall down. And that guy was like standing on the wall and his head was pointing into the middle. Okay? And that's all like super realistic, super practical. It's also how we would want to generate artificial gravity. Okay? You guys live in the time where science fiction has to be a lot less fiction and more science. Okay? Back in the day, when they made science fiction, it was all about fiction and just a little bit about the science. So artificial gravity was this thing that they had. Okay? Like people just walked around, they didn't fly off because they had artificial gravity. Nobody cared how, it was just there, because that was easy. You just said that you had it, and it worked. Okay? Well, you guys are a bit more of a picky audience, let's say. Okay? Well, how is it there? How does it work? So now all the modern science fiction movies, they've all got a part of the ship that, well, you guys haven't seen very much science fiction. You guys seen The Martian, right? If you haven't seen The Martian, first read the book, then watch the movie. The movie's good, the book's better. Okay? But there's always a part of the ship that spins. Okay? And it spins because that works just like the gravitron. If you're on the inside of the spinning ring, your inertia wants you to go in a straight line, but the floor keeps you from doing that and pushes you back towards the center. So you don't really have weight. Okay? There's no gravity per se, but there's this centripetal force from the floor that pushes against your feet and feels just like normal force on Earth feels, a push against my feet. Okay? That sort of makes sense? Okay? The idea has been around for ages, but we still don't do it. Why don't we have a part of the International Space Station that spins around and around? It's easy in concept, it's really hard in reality. Because if you have any part of a space station that spins, there's a Newtonian reaction to that that tries to make other things go. Right? It's conservation of angular momentum. You can't have one part of the ship that spins, because there's got to be something that's spinning it, and there would be a reversing force somewhere else. It causes a lot of torque. Okay? And so we have to be mindful of that if we're building something like this. Okay, why do we need to have artificial gravity? Why would that be important if you're going to be in space for a really long time?
So when you come back to Earth with gravity, you're not pulling just
Yeah, it's a lot about returning to a gravity environment. Zero gravity is really, really hard on the human body. human body did not evolve in a zero gravity environment. It evolved in a 1G environment. And a lot of how our body works depends on gravity. So when it's suddenly gone, our body does a ton of weird stuff. Okay? Our bodies are the ultimate recycler. So if you don't use something, your body recycles it. If you don't use it, you lose it. Okay? And so that goes for your muscles. When you're in space and you're weightless, you don't use your muscles nearly as much as you do on Earth. Okay? Like right now, standing, even you sitting, you're using your muscles. You're fighting gravity right now, because if you don't, you fall over. I know this because I've seen people fall asleep in my class, and they almost fall out of their chair. Okay? And it's funny. But it's funny, tragic, but it's still what happens. Okay, you have to have your muscles tense, you're fighting gravity, you're turning and moving, all of that fights gravity, and so they're always doing something, especially your heart muscle and the muscles of your thoracic cavity and diaphragm, okay, the ones that help you breathe. In zero gravity, those muscles don't have to work at all. Okay? Your heart is now pumping blood that doesn't have to be that isn't being pulled back down because of gravity. Okay? Your chest now is weightless, so your lung muscle, the muscles around your lungs, okay, they don't have to work nearly as hard to lift your chest to ventilate and let it go. Okay? So they atrophy. And if you don't do anything about that, when you return to Earth, you can barely breathe, and your blood pressure drops because your heart has gotten weak. Okay? They discovered this after the Soviet Union collapsed. When the Soviet Union collapsed, there were still astronauts up on the Soviet space station. Okay? The Soviet Union was done. Russia wasn't kind of there yet, and there was no money or equipment to send supplies to these guys or bring them back. So the Americans obviously right away went, hey, we'll go up there. We want to get a look at your stuff. Okay, we'll go up and get your guys, no problem. And the Russians are like, hell no, you're not doing that. That's Russian soil. You can't set foot on there. I mean, we may not be country anymore, but you don't step on our place. Okay, so they wouldn't let them go up there. But what they did allow was unmanned supply missions to be sent there, so the guys didn't starve or die of thirst or whatever. But they were on there for a very, very long time, like over a year. When they came back, they had to be put on ventilators because you couldn't breathe. Okay? They got into the gravity environment and they were so weak, okay, they could barely move, even not really breathe. So they had to kind of slowly gain back their muscle mass. So what you wouldn't want to get on a spacecraft and go to Mars, which takes 6 to 8 months, and then get to Mars and be a weakling, instead of getting out of the spacecraft and putting the first footprint triumphantly on Mars. You're so weak that you trip and fall and smash your faceplate into the soil and go, well, that's one big blub for mankind. Okay, like it would be pretty embarrassing. So these are all things that they have to consider, and that's just one of them. Okay, is muscle atrophy. There's a lot of other stuff that goes on in your body as well that's dependent on gravity, and a lot of it has to do with your balance. What part of your body does your balance? Oh, sorry, that maintains your balance. Where's the balance center? Actually, just below the brain. You ever get an ear infection? Get dizzy? That's why. Okay? The middle ear is where your balance center is. Okay? And so when we turn our heads or we tilt our heads or we're doing something, the inner ear can detect, because of gravity, that we're being pulled in a different direction, and it'll automatically tell our core, tense these muscles so we don't fall down. Well, when you get into space and there's no gravity, the inner ear is like that car alarm in your neighborhood that never shuts off. Okay? It's screaming at the brain all the time. We're turning, we're sideways, we're upside down, we're right side up, we're upside down again, we're turning, and the brain finally just goes, shut up, and it just stops listening to the balance center in the ear, and goes to the eyes. Okay? So the eyes can tell the brain, okay, this way is up, this way is down, and gives it some perspective. That's great in zero gravity. You get back into a gravity environment, brain's still relying on your eyes. So now you're in gravity, you look down, you fall down. Okay? Because your brain is going, oh, eyes told us that we're straight, except we're not. Boom, down we go. Okay? And so it's a big deal. When they're bringing astronauts back from space, they always escort them. They've got one person on each arm. Because if someone talks to them, like calls their name and they turn this way, they'll just walk. They'll just go that way. Okay? Because their brain is still relying on their eyes for balance, and they can really like hurt themselves. They fall often, so they have to be escorted around until the brain starts listening to the middle ear again. Okay? It has to almost be retrained when they come back. Okay? So there's a lot of stuff that goes on. Your bones are another thing. Okay? On Earth, our bones are always getting microfractures. And even just walking causes little tiny microfractures in the bones, and then they heal and they get stronger. Okay? That's why they tell like elderly people with osteoporosis, you need to walk. Just go for a walk every day, and it helps to build up their bone density. Well, when you're an astronaut in zero gravity, you come back to Earth, like Chris Hadfield, he came back to Earth, his bone density was that of like a 70-year-old man when he got back. Okay? And that was after doing all the exercises and things like that that they do on the International Space Station to try and maintain that. Right? So zero gravity is really hard on the human body. If we're going to have astronauts going from one planet to another, we have to simulate gravity for their health. Okay? Otherwise, they realistically could die, be very, very unhealthy. Right? And that's not good when you're millions of kilometers away from the nearest hospital. So it's a big problem. So we gotta figure out ways around it. Right? So there's all kinds of stuff here: loss of blood plasma. Okay, weight-bearing bones and muscles deteriorate. Kidney filtration rate increases. You can get kidney stones. Okay, they have to watch their calcium intake because their bones are being broken down. Okay, all that changed sensory input that we were talking about. Being in space also means you're exposed to more cosmic rays, and your risk of cancer is much greater. Well, that has nothing to do with gravity, but okay, there's all kinds of things. Touch sensors, okay, and things like that in your feet work differently because again, there's no gravity pulling down on you. You'll lose the calluses in your feet. Okay, like everybody's got calluses on their feet. You lose those in zero gravity because you don't use it. Okay? Yeah, so there's all kinds of kind of issues with being in zero gravity. So the idea of artificial gravity has been around for a long time. Okay, so I'm going to show you a few of Chris Hadfield's videos from when he was on the International Space Station, and it's how everyday things are so different in zero gravity. Okay, like here's the one everybody asks about, but they can never show. The space toilet. Think about how much you depend on gravity in the bathroom. It's not something you normally think about. You take that for granted, that everything that comes out of you just falls away from you. Okay? It's very convenient to have gravity in the bathroom. Zero gravity, the Space John's got to work a lot differently. Okay? The Space John has this, well, they say it's windy in the Space John. Okay? Because they actually have to vent to outer space a little tiny bit to create a suction. All right, so everybody has their own tube, okay, that they use in order to pull all the liquid and solid wastes away from them in the bathroom, because otherwise, well, it would float. That would be gross. Okay. Another thing, vomit. Okay, if you're in your, like this is one of the reasons why there's such big physical tests on astronauts. If you're in zero gravity and you're in a spacesuit and you vomit, you'll die. Why? You'll drown. Yeah. Okay. If you vomit in your spacesuit and there's no gravity, the vomit will stay in front of you, and when you inhale, you'll inhale the vomit. Okay, and that'll kill you. Right? You get all that acidic vomit into your lungs. If it doesn't choke you, it'll destroy your lungs. Okay, and so that's a really big deal. And gravity, you take it for granted all the time. Okay, so I'm going to show you a few of the ones that. So to make artificial gravity work, you basically have to have some part of the ship that is a spinning drum. Okay, and you put the people on the inside of the outer edge of the spinning drum. That way, as the drum spins, your inertia wants you to go in a straight line, but the floor, the inner part of the drum, pushes you back towards the middle. Okay? Now, that means that you could actually adjust the amount of gravity that you feel. Right? Either the radius or the rate of spin is going to affect how heavy you feel. So if you're on a mission to Mars, you might be wanting to acclimate to Martian gravity, so you might have it spin a little bit slower so that you feel Martian gravity, you get used to how your body works and how you move in 1/3 Earth gravity, okay, so that when you get there, you're not clumsy. Okay? And then maybe on the way back, you're thinking about getting back and going to the beach, you want to look good, so you crank it up to like 2 Gs, so everything's twice as heavy as normal, and you get jacked on the way home. Okay, you probably wouldn't do that, but okay, you could adjust it to be heavier than normal and get back into shape, okay, on the way back. Right? But that's the general idea for how artificial gravity would work. And like I say, that idea has been around for a very, very long time, even as far back as like the 50s. Okay? Anyone seen the movie 2001: A Space Odyssey? It's even older than me, so it's like really old. Okay? But the special effects in it, they still hold up. They have all these shots of all these ideas because this is stuff that Arthur C. Clarke, the guy who wrote the book, knew about because he was actually someone who worked for NASA for quite a while. So a lot of his ideas that are in his books are actually things that happen now. Okay? It's weird to watch something made in the late 60s and just see how it holds up, like how those special effects shots that were all practical, there was no CG, they work, and the ideas that they have, how they are actually true and work in kind of a modern state. When did this period end? Was that 1058? Yeah. Oh, right. I don't have time to show you the video, but I will show it to you on Monday. I'll have you guys pack up because I need to wipe down your desk when my grade 4 class gets here.